These are the frequently asked questions for Algebra 2 for section 7-6, day 2. We'll look at number 30 here. And 30 says we are to use natural logarithms to solve each equation. They really wouldn't have had to tell us that. We can see that we have a base of e in this problem. So what we have to do is we have to isolate that base of e, and that'll mean subtracting 4 from both sides. So e to the x over 5 power is going to equal 3. And then we think, okay, well, now what do I do in order to get rid of that e? Well, that is logarithm base e, and remember that is natural logarithm. So we take the natural logarithm of both sides, and that is the inverse of a base of e. So this will give us x over 5 equals the natural log of 3. And then we would multiply both sides by 5 so that these two would cancel out. And back here we would just use our calculator and find 5 times the natural log of 3. So that's the part we need right there, is 5 times the natural log of 3. And that comes out to 5.49306. So that will be 5.4931, rounded to the nearest thousandths position. All right, then the next one that I have up here is number 37. And for 37, we again are going to start by trying to isolate that base of e. So we would subtract 7 from both sides, negative 2, e to the x over 2 equals negative 6. And then we would go ahead and divide both sides by negative 2 because, again, we need to isolate that e base. So this will be e to the x over 2 power equals 3. And again, we need to get rid of that e so we can gain access to the x, and that means we're going to take the natural logarithm of both sides. And because e as a base and natural logarithm are inverses of each other, we get x over 2 equals the natural log of 3. And then we would go ahead and multiply both sides by 2, being very careful not to put the times 2 in the back. We want the entire natural logarithm of 3 to be multiplied by 2. So over here we'll have x, and on the other side 2 times the natural log of 3, and that will give us 2 times natural log of 3 on the calculator is 2.1972. And there it is. So with these, just remember, you have to isolate first, and then use logarithms, natural logarithms in this case, to undo that base of e. Then we start in on some word problems here, and this one is kind of a monster of keeping track of everything. So as you go through it, for exercises 38 and 39, using this formula right here, where v is the velocity of the rocket, so you have to remember v, velocity of rocket. Then we have t, which is the firing time. Then we have c as the velocity of the exhaust. And we have r as the ratio of the mass of the rocket filled with fuel to the mass of the rocket without fuel. We can just think of that one as the ratio of the masses as we go through that. So for number 38, it says, find the velocity of a spacecraft. So I know I'm supposed to find v. So I'll just start writing the rest of this down, 0.0098. And now I'm looking for t. And again, t stood for the firing time. So I keep reading. It says it has a mass ratio of 20 and exhaust velocity of 2.7. There's what I need. There's that firing time. So put that little 9.8 up here, and then the 30 seconds. Next thing I need is c, and c is the velocity of the exhaust. Exhaust velocity, 2.7. And one more thing to look for, r, and that's that mass ratio. And it tells us this one has a mass ratio of 20. And I realize this can just be totally punched into the calculator. So negative 0.0098 times 30 plus And then I probably, just for safety's sake, would use parentheses on that last portion there. And that comes out to 7.79 kilometers per second. And they ask us whether or not that can achieve a stable orbit 300 kilometers above Earth. And reminder, we went through the example in class and it told us that 7.7 kilometers per second, that was the cutoff. Well, we're higher than that at 7.79, so the answer is yes, that can achieve that stable orbit. Number 39, this one says the rocket has a mass ratio of 24, an exhaust velocity of 2.5 kilometers per second. We are to determine the minimum firing time for a stable orbit 300 kilometers above Earth. So we're looking for T this time. And they said this one has a mass ratio of 24, so there is our R value, and an exhaust velocity of 2.5 kilometers per second. So we go back up and take a look and see, oh yeah, exhaust velocity, that was C. So this is going to be C. Determine the minimum firing time for a stable orbit 300 kilometers above Earth. So we're kind of looking around saying, where's V? You know, where's the velocity? We know what it is. It has to come out to at least 7.7. All right, 7.7 in for V, and then we have the negative 0.0098, and then we needed T, and T was the firing time. So we go back to the problem and we realize, hey, that's what we were supposed to find, so there's our T, and just keep going back to the formula so that you can see where everything goes. Then we have ClN of R, and C was 2.5, natural log of 24. All right, so now we need to solve. So to solve this, we have our little 7.7 over here. We are going to have to subtract 2.5 natural log of 24 from each side. So that will be out of there. And then we will have to divide everything by negative 0.0098. And I skipped a step up here, and I probably shouldn't do that because if you're watching the FAQs, you may have needed that step. Remember, this is just a number up here, the negative 2.5 natural log of 24. We're just subtracting a number from both sides, and then we are dividing. And this one, yeah, you're going to want to be a little careful when you punch this one in. You want to use at least double parentheses up there, possibly triple if you're going to punch it in all at one time. And when you do that, number 39 comes out to 25 seconds. But that is the very least it could possibly be, because remember, we have to meet that 7.7, so you might want to put at least 25 seconds in there for number 39. Like I said, that's kind of a monster of a formula, but it works. Then, number 40, speaking of monster formulas, by measuring the amount of carbon-14 in an object, so carbon dating, a paleontologist can determine its approximate age. The amount of carbon-14 in an object is given by this lovely little formula right here, where A is the amount of carbon-14 originally in the object, so kind of the initial amount, and T is the age of the object in years. In 2003, a bone believed to be from a dire wolf was found at the La Brea tar pits. The bone contains 14%, and that's going to be 0.14 of its original carbon-14. How old is the bone? Well, let's put all this stuff where it's supposed to go. So what we have here is the 0.14. And then it said A is the amount of carbon-14 originally in the object. Well, that would be 100%. So that's a 1. And the 1 isn't going to do anything to maths, but we'll put that in there anyway. And then we go back to the formula and we have negative 0.00012 T. And we realize, well, because that 1 isn't doing anything over there, we could just jump right to taking the natural logarithm of both sides, because we need to figure out T. So these are going to be inverses of each other, and we'll get negative 0.00012 t. And over here we have the natural logarithm of 0.14. And then finally we would go ahead and divide by negative 0.00012. And that will give us the time, and this comes out to 16,384 years and some change. But that's about how many years we would need there. And the bullets kind of take you through what numbers should you substitute for y and t, and what properties could you use to solve the equation, and there we are. Then number 41 tells us that a fossil bone contains 25% of its original carbon-14. What's the approximate age of the bone? So with this one, we're going to put in the 0.25, and I'm not even going to bother with the 1 this time because that's 100% of what it was. So e to the negative 0.00012 t, and it is the same type of math that we just did for the first problem. We need to gain access to the t, so that means this base of e has to go. And that is the inverse using that natural logarithm. So we'll have the natural logarithm of 0.25 equals negative 0.0012 t, and then we'll divide by negative 0.00012. All of this we just kind of bring along so that we don't have a rounding error. We wouldn't want to punch something in and then round it and then do some more math and then round again, because we will have a rounding error. So this one, 11,552 years, approximately, for the carbon dating. Number 42 says simplify each expression, and I love these because it makes you think about the process of the lengths that we go to work with numbers in mathematics. This is a logarithm base e of 1. And you think, okay, well, how am I going to get that to happen? So it equals something, I don't know what it is. E to the x equals 1. Well, e to the 0 always equals 1. So this is just a very cool way for us to write 0, natural log of 1. And then in number 43, if you take a close look, you see, hey, wait a minute. The natural log of e, that's an inverse. It's 1. That's 1/4. In number 50, we have inverses again. Natural log of e to the 3rd, those two will drop out, and we will get 3 for our answer. 51, natural log of e to the 4th over 8, inverses. So 51 will be 4 over 8, which is 1/2. So very cool ways that we come up to work with numbers in mathematics. Not done with the word problems yet. We're getting close, but not yet. Use the formula for maximum velocity. It's the same one we saw earlier. Find the mass ratio. So this time we want to find this right here. Of a rocket with an exhaust velocity of 3.1 kilometers per second, a firing time of 50 seconds, and a maximum shuttle velocity of 6.9 kilometers per second. So just a reminder here, v is the velocity of the rocket. C is the exhaust velocity. T is the firing time. And last but not least, R is the mass ratio, and that is what we're interested in getting. So let's see what we have here. It says it has a velocity of 6.9, so that's going to go in for V. And then we had a T value up here, firing time of 50. And we have an exhaust velocity of 3.1. And we want to get R, that mass ratio. So what do we need to do? Well, we need to add whatever 0.0098 times 50 is, and that comes out to 4.9. So this is negative 0.49. Wait a minute, 0.49. My decimal in the right spot. There we go. So we're going to have to add 0.49 to both sides, because when you do this multiplication, you get negative 0.49. And that gives us 7.39 equals 3.1 natural log of r. Well, then we have to divide both sides by 3.1, and this does not work out nice, so this I'm going to wait to do my punching in for until the very end. And now we get to this point, and we want to get rid of natural logarithm. Well, what we have to do is we have to write this as the natural log with a base, and natural log is e for base. So logarithm base e of r equals 7.39 over 3.1, and then snail shell, e to the 7.39 divided by 3.1 power equals r. And then you take a second and you punch that little monster into the calculator, and that gives you an r value of 10.85 for that mass ratio. So using the same formula throughout many problems here, but just using it differently, finding a different variable. Then biology, it says the formula h equals 1 over r times the quantity natural log of p minus natural log of a models the number of hours it takes a bacteria culture to decline, where h is the number of hours, r is the rate of decline, p is the initial bacteria population, and a is the reduced bacteria population. So we could do some manipulation here and do a little condensing, but I would think most people would just like to just use the formula and put everything in. So this says we have a scientist that determines that an antibiotic reduces a population of 20,000 bacteria to 5,000 in 24 hours. Find the rate of decline caused by the antibiotic. So we look up there and it says it models the number of hours it takes a bacterial culture to decline. H is the number of hours, all right? So we look through this and it says, hey, that's 24 hours. So we've got a 24 equals, and then we have 1 over r. So we're looking at r, and r is the rate of decline. And what we want to find is that rate of decline. Initial bacteria, 20,000. And final, 5,000. So now we will get 24 equals. I don't really like the 1 over r thing, so what I'm going to do is just look at that as dividing by r. And we have a subtraction going on with our natural log, so we could put that together too. But basically this is all one number, the natural log of 20,000 minus the natural log of 5,000, because we could certainly punch that into our calculator. So at this point, you have a choice about what you want to do. You could slap a 1 underneath here, and you could cross multiply, because you have to get your r out of the denominator. That's what we're trying to solve for here. So if we cross multiply, we'll get 24r equals the natural log of 20,000 minus the natural log of 5,000. All right, so have the cross multiplying there. 25 times r equals natural log of 20,000 minus natural log of 5,000. And then the last thing that I would do is I would just say, oops, come on, smartboard, behave yourself. Put that back where it was. Natural log of 20,000 minus the natural log of 5,000. We're going to divide both sides by 24 to get r all by itself. And really, at this point, we kind of see what's going on, but we can go ahead and punch it all in. So natural log of 20,000, and then we need that. We need to subtract the natural log of 5,000. Don't forget your parentheses after you punch those pieces in. And we divide it by 24. And r comes out to 0.05776, etc. So approximately 5.8%. And as I said, I guess I'm going to probably go through it anyway. There's a different way to do this, because we see right here that we have 2 natural logarithms with subtraction. So you could say, hey, subtraction's division, so I really need 20,000 divided by 5,000, which is of course 4. So you could write this as the natural log of 4 over 24, and if you punch that in, you'll see, hey, I get exactly the same answer. So it depends on whether or not you want to manipulate the formula before you start, you want to manipulate it somewhere during the process, but that manipulation in this case is going to be condensing. So whatever makes the math easier for you, you do. So in 59, I take a different look at this formula and say, okay, let's see, how can I get stuff to be a little bit easier to punch in here? And it was h equals 1 over r times the natural log of p minus the natural log of a. And we realize, okay, what's really happening here is we're going to take the natural log of p divided by a, and then I can just divide that by r, because that's what multiplying by 1 over r does. So then we figure out what information do we have in 59. And in 59 it says the rate of decline was 0.14. So that is our h value. And then it said it started at 8,000 and it shrunk to 500. So we're going to need the natural log of all of that, and we need that over r. And again, you could just cross multiply at this point. Slap a 1 under there, 0.14 times r equals the natural log of, and then you could figure out, hey, wait a minute, 8,000 divided by 500, that's 16. And divide by the 0.14 to get your r value. So again, don't forget to punch in your parentheses. So natural log 16 parentheses divided by 0.14. If you don't finish those off, the calculator does not know to stop with all of the logarithm business. So 19.8 hours is what we see for that one. Number 66 says an investment of $750 will be worth $1,500 after 12 years of continuously compounding. Continuously compounding is our sticky green shampoo formula, PERT. Now I just sang a little song about how unhappy I am with my smartboard, but let me get going on this again. When we have continuously compounding, that's going to be our stinky green shampoo formula, PERT. And we want $1,500, starting with $750. Interest rate we don't know, but we know it took 12 years. So we need to divide both sides by 750, and we'll get 2 equals e to the 12r. And then we need to take the natural logarithm of both sides of this. So the natural log of 2 equals, these are inverses, 12r, divide both sides by 12. And r is 0.057. Let me get that here real quick on my calculator. Natural log of 2 divided by 12. 0.05776. I'm going to round that to 0.058. So approximately 5.8% as we go through that. All right, this took a while because the smartboard was having some issues, so that should be it for this section.